Thank you. Okay, what is this? Okay, so the topic of my presentation will be indeed, I will present you a device that with a number of colleagues we have developed, and we did experiments on that starting from a couple of years ago. And this device has as it's written in the title, our goal is to attenuate surface gravity waves. So the idea is to try to avoid the problem of beach erosion, as I will tell you how relevant it is and why it is so important to take care of that. So before jumping into the topic, I mean there are a number of collaborators and young people, but also senior people, because this is a collaboration in which we have done some both experimental work. So you need experimentalists, you need people who live in lab, and on the other side we have also done some more theoretical work, some analytical work. And so this is the list of people which has contributed to in different manners to what I will talk about today. So okay, let me go. Okay, so this is the outline of the presentation. So I will start by giving you some motivation. So why we want to develop that, and now we'll go a little bit on the state of the art of the devices that nowadays are used to protect the beaches from erosion. And then the next step is going to be the presentation of our device, which we call Metareef. Meta is indeed stands for metamaterial, because as well as you will see is based on the concept of metamaterials. And then I mean it's quite difficult to let's say to make it to describe it from fundamental mechanics, in the sense that this is a very tough problem, because we have objects as you will see that move underwater under the influence of waves. So you have a free surface, you have objects that move. So from a, let's say, mathematical point of view, this is rather a difficult model to handle. We can do, as you will see, some numerical computation, but fully, I mean, DNS, direct numerical computation. But in order to understand what is happening, it's constructive to use a toy model. So that's what I will do. I will introduce a simple toy model for understanding the physics of this of Metareef, but of course it will be only qualitative, but it help. I mean, I think it's also good for I mean, if students are present, to make students understand what is this, the concept of Metareef. And then I will go over some experiments in WaveTank that we have done recently, and I forgot to mention here, but also some numerical computation. I will also present some numerical computation, and at the end will be some discussion and conclusion. So let me go over this this problem. So this is the problem of beach erosion. So the idea is the following. I don't know why I say this. Let me just. Okay. So I mean, the population, most of the population on Earth live by the coast, and but coasts at the same time are the most vulnerable areas in our planet. You know, and especially nowadays, that because of climate changes, the level of water is rising, and I mean, I've been talking just a few days ago with a colleague who's a climatologist, and he mentioned it. But now, by now, it's quite clear that by the end of the century, we will have half a meter of of water level rise in our ocean. So that's something that people should care about. But in any case, what and this is not what I will talk about in this presentation, but I'm more interested into the role of waves that have on beaches. So the idea, the plot that you see here, which has been quite inspiring, is a plot that comes from a paper by Louis and Dick. It's published in Scientific Report, and it's called The State of the World's Beaches. And here you see, all the coastline, and you see different dots. You see, first of all, green and red dots. And when you see green, this means that the beaches are actually getting bigger and bigger. Okay, so you have an increase of the sand in the beach. But when you see red, what actually is happening is that when you see red, it means that there is a problem of erosion, and you see that there are different size of the bullets. The smaller one to the large, very large one, and those are related to the rate of erosion at which the beaches are indeed eroded. So one of the conclusion of this paper is that 24% of the world's sandy beaches are persistently eroding at a rate of exceeding 0.5 meters per year. And this has been a study over 1984 to 2016. So this is the status. Of course, as I mentioned, there is a big issue related to water level rise, but what we mainly are interested in what I will present you is related to the waves and to the effect of the waves on the beach. Indeed, when waves continuously break on the beaches, what happens is that they can, well, of course, they can move sediments, they can transport sediments, they can create currents along the shore, they can transport sediments. So really, this is what is happening, and so people are really taking care of these problems. And so now, what are the things? What are the devices that usually are done by humans? So there are two types. I mean, those are the major kind of devices that are placed. So there are breakwaters and groins. So the breakwaters is what you see on your left. So basically, they're made of rocks. They're built parallel to the coast, as you see here. And of course, because the effect of this breakwater is to reduce the incoming wave energy, right? Because waves would break on them, and so they provide a shelter beach area, and they shelter also vessel. On the other side here, you see groins, and those groins are structures which are built perpendicular to the shoreline. So as you see here, right? Those are, they work differently in the sense that what they do, and they are built to avoid a long shore drift or currents, which so they're, because as I mentioned, waves don't really break all the time with their crest parallel to the coast. So what happens is that they inject a momentum, a transverse momentum, so they create currents, and these currents can carry sediments along the coast. So this is why those groins are usually placed in some coastlines. Okay, but let me just a little bit mention some of the. Of course, I mean they do their job. I mean, absolutely. In terms of protecting the coast, they really do their job, because you see breakwaters here. Waves do not go to the shore, so they really are protecting the beaches. But on the other side, there are some disadvantages that I want to highlight in this slide. So what happened is that, and people who in Italy, we have a number of these breakwaters in the Adriatic Sea. And one of the main issues is that the water that is here behind just the breakwaters, it deteriorates in the sense that the quality of the water is not as good. And those breakwaters, what they do, they actually increase the turbidity of the water. then it can happen also that at the ends of the breakwater, due to the effect of incident wave motion, seabed becomes deeper, creating also danger for bathing. But also debris may accumulate on groins, okay, because they, they are transversal structure. So if you have currents, what happens is that debris can accumulate actually on those groins, and this can be a really problem for marine animals and plants, of course. And also, it has been shown that the presence of groins may create rip currents that can be, very dangerous for swimming. And for sure, one of the things that is most relevant to me is that the visual impact of groins and breakwaters is quite high. So this means that there is a non-negligible consequence for the attractiveness of tourist resorts, right? I mean, if you place one of this breakwater in front of a beautiful beach in Sardinia or in Calabria, you're sure that you will make this place less attractive than other places. So this is why, I mean, we came to our idea. So the main idea that we came is to develop some device which actually is not visible from the coast. So that's one of the most important thing that we have been thinking about. And the idea is the following. I mean, what we have here is basically is based on the fact that we place underwater pendula which are made with materials which are floating materials. So basically, those are tethered at the bottom, so they can oscillate with some frequency, and they're placed at some distance one from each other. In this case, for example, you can imagine the waves are coming from the left, right? And so what happened is that waves, ocean waves, you know that they have not only potential energy, so there is not just a displacement of the surface elevation, but what is happening is that there is also some kinetic energy of the wave. So kinetic energy associated to the waves. So basically, there is a fluid moving under the waves. And what is happening is that under the influence of these waves, this pendula will start oscillates, more or less like the molecules of water in food when you place it in a microwave, right? They will start oscillating, hitting the food. In this case, they will start moving. And basically what will happen is that because they move in a fluid which is viscous, and the Reynolds number is sufficiently high, they will create a wake, which can be turbulent. And then you have a kinetic energy, turbulent kinetic energy. You will have a cascade, and at some point you'll dissipate all that. So part of the energy of the wave will be dissipated through turbulence, okay? And that's the first thing. And this is going to be especially true when the frequency of the wave is comparable to the frequency of oscillation of the pendulum, right? Because each pendulum has a frequency of oscillation which is related to its length, right? And to the gravity, which is in this case is upside down. It's a reduced gravity. So actually, the force is oriented towards z, positive z, and so yes, this is what if the frequency of the pendula is comparable with the frequency of the waves, of course, we will have an excitation of the motion of this pendula, and this will extract energy from the waves. This is quite natural, just like as I mentioned, food in a microwave. Of course, the dish will not be heated because the microwaves are of the same frequency as the frequency of oscillation of the molecule of water which are inside the food, and this is how it works. But more than that, there is also another mechanism. If you displace, this would hold for a single pendulum. But actually, if you place more of them, you place them in an array, in a lattice, as you will see, we will have also collective effects. In particular, we can have effects related to the Bragg scattering, which is a typical effect of in solid state physics, by which waves can be reflected. And this reflection can happen at certain distances when the waves is related to some certain distance between the pendula. But we will go into the details of that. So this is what it would look like. Okay, so you have waves coming from the offshore. You have our array, and then you have the beach, and then the hope is that this will be able to protect from the coast. Beside application, I would like to mention that this has been also an interesting study from a physical point of view, because there are different mechanisms which are actually interesting and not so clear. In any case, we have patented, and so there is a European patent for this, which is this number that you see here. Okay, so let me go through what I believe are the advantages of Metareef with respect to other solutions. Okay, so first of all, the uniqueness of the Metareef consists in the fact that the proposed device is completely submerged. So you cannot see it from the coast. So that's something good, right? And also, the impact on the environment is surely reduced, because you will not have any more these zones behind the breakwaters where the water becomes dirty and so unpleasant for taking for swimming. It has also very low impact on the marine life, in the sense that plants can grow, vegetation can grow, fishes, small fishes can clearly go around, and there is also a limited gray material consumption, so less concrete, rocks. Also, the currents should not be, should not be altered, should not change the local currents. And apparently, we haven't made really a rigorous study on this, but it seems that it's much more the costs for producing this device are limited with respect to groins or breakwater due to their simplicity. So basically, you have to anchor just pendula, right? So that's I'm not saying that it's something simple, but can be simpler than building a breakwater using concrete and rocks and so on. But of course, there is a main question that I want to give you an answer on this, at least an answer that I can get from experimental data in a wave tank, which of course is not the ocean, so it's not surely the end of the story. But of course, if we want to present this as a device that is working for attenuating surface gravity waves, we need to have something that actually attenuate as well or almost as well as the breakwaters, and so I will show you at what level we are at the moment. Okay, so just to keep going on list of things, and as I mentioned, the word meta comes from metamaterials. Indeed, the Metareef is based on the concept of metamaterials, but what are metamaterials? Basically are materials which are engineered, which are, and they are able, the idea is to be able to change the properties of a wave. So basically what you want to do, usually you want to change dispersion relation of the waves, you want to change their, you want to reflect waves, you want to, diffract waves in a way to, to do exactly what you want the wave to do. So that's why you put those structures, which are usually periodic structures, which are placed at a scale which is smaller than the wavelength of the phenomena, right, the influence. So we have to place, if you have wavelengths in the ocean, which are, let's say, 100-meter wavelength or 50-meter wavelength, you have to place definitely those objects if you want them to act as metamaterials on a scale which is smaller than the wavelength the waves in the ocean. So as I mentioned, they can block, absorb, enhance, bend, change speed of the waves, all these properties that you want to play with. And of course, our main idea is to try to block and absorb waves, right? We don't want to. Another idea could be to bend waves, and also we did some preliminary work on that, or change direction of propagation. But what I will present is basically blocking or absorbing waves. Metamaterials is quite, I mean, it's already an old concept, but it came out mostly in electromagnetic waves, but there are plenty of, application in acoustic and seismic. So the idea, for example, in seismic is to put metamaterials around some structure that you want to preserve. It could be a castle, it could be a church, could be whatever. You place metamaterials around it, so seismic waves will not be able to go through, right? Or elastic waves, or also there are some application to waterways, but I don't think there are many applications. There are just a limited number of papers. Although, again, already in the 70s, people were trying to study the evolution of, for example, water waves on a seabed on a periodic structure, right? With fixed periodic structures. That's a typical problem that you can find. Maybe I'm not sure in the book of C.C. May, but definitely C.C. May has written about it. So it's quite an old problem, right? The interaction of waves with some floor seabed that is periodic, but as I will show you here, we have something more, which is basically the idea that you have resonators in the system. Metareef is also bio-inspired. We have been partners of University of Torino, have been a partner of a big European project of bio-inspired metamaterials, which was called Bohème. And inspiration for this oscillating objects actually came from, although this is just very qualitative in the sense that there is nothing quantitative in this case, but from the Posidonia oceanica, which is a seagrass, which is a plant in the ocean. And I'm sure that Francesco knows about it because this is typical in the Mediterranean coastlines. And it seems that, I mean, according to a number of studies that have been made, for example, I took this, which is by Koftis and Prinos, it seems that it plays an important role in protecting the Mediterranean coastline from erosion, in the sense that those plants, the seagrass, actually oscillate and somehow oscillate when wave goes through. Again, it's not exactly the same mechanism that we have, but oscillating, they shelter somehow the beach, and through some mechanism which is more related maybe to viscous effects, they are able to protect the coastlines. So those are just very general concepts and idea that I would like to present you. And now let me go through a very simple, I mean, as I mentioned, if you want to do modeling this problem from Navier-Stokes equation, or again, our device from Navier-Stokes equation, this is quite complicated. I mean, you can write down equations, you can solve the DNS, so you can do direct numerical simulation. It's not simple, but a colleague of mine, Francesco De Vita, I think, who is also in listening online, he was able to develop a code that was able to do that, and I will present a few slides on that. But if you want to learn something about it, and if you want to teach somebody how does this device is working, I think it's much better to go to models which are much simple, and we can understand how things are working. And this is the toy model that I'm presenting. So now, I mean, water waves, they oscillate transversely to the propagation. Actually, they're not fully transverse wave, but here I just imagine to have not transverse waves, but longitudinal waves. So I have a system of masses and springs. They are connected. This is a linear problem. You can make it nonlinear. This is a very famous problem, which is called Fermi-Pasta-Ulam Singo problem, but I will not discuss about it. But in any case, you can have by compression and rarefaction of this masses of the springs. Yeah, you can propagate waves. So you have to imagine that those waves are the one. Although this is a discrete system, you have to imagine that these are waves that propagate on the surface of the ocean. All right. So in order to understand it, here it's much simpler. So you can write really, and I mean, we all know that the forces between the two adjacent masses is just given by the Hooke law, which is chi, which is the stiffness of the spring, and delta Q is the distance between. I mean, Q is the displacement with respect to the equilibrium position. So delta Q is just basically the distance between the two masses, right? So the relative distance between the two masses. This system is Hamiltonian. So again, we try to understand things from an Hamiltonian point of view without introducing viscosity, so we have a better understanding of what's going on in the system. And here you have kinetic energy. P are just momenta, Pj are momenta, and Qj are position. So you can write the equation of motion, right? So those are linear equation of motion, as I mentioned. So this is Q dot dot J. J is the pendulum number J. You have n of these equations which are coupled to each other, and this is I mean, if you can recognize this as a second order. I mean, if you go into some continuum limit, this is going to be the second derivative in space. So this, in some approximation, reduces to the D'Alembert equation. But however, if you take it as it is and you assume periodic boundary conditions, so you plug in, Fourier discrete Fourier transform, you're able to rewrite this in terms of harmonic oscillators in Fourier space, and so you're able to find the dispersion relation with it, which is this one. So this is the dispersion relation typical of this system of masses and springs, right? So what we learn from here, basically, we learn that frequencies with these are non-dimensional units. We have, well, I mean, arbitrary unit, basically. We have chosen chi and m equal to 1, okay? So basically what we learn is that for frequencies larger than 2, you are not allowed to propagate waves in the system, right? But all the other frequencies between 0 and 2, they are allowed to propagate, right? So that's what we learn from this dispersion relation. But now, okay, we want to do something which is now similar to our device somehow. So what we do, we introduce, and now we do it for each mass, we introduce a resonator, which would be like our pendula. So you have to imagine that this is our pendula that is placed underwater, right? And for each mass, so we have an extra pendulum. So this is not a two-dimensional system. It keeps being a one-dimensional system. So waves will, masses will only oscillate horizontally. But it's clear that if you have a spring here, if I oscillate this mass MQ, this mass MR will start oscillating as well, right? So basically, it's like the water waves that when they pass, they excite the dynamics of a pendula, which is underwater. Right. So, as I mentioned, this is only qualitative, but it's very helpful. At least it was for me for understanding what's the physics of this problem. So basically, you can write down the equation of motion, and you can write the equation of motion. These are fairly the same equation of motion as before for variable Qj, and Rj is the displacement of the red masses, right? And Qj is the displacement of the blue masses. And as you can see here, there is a coupling in between because it's given by Rj minus Qj, and so the forces on the Rj masses Rj is just given by this difference by Rj minus Qj with a minus sign here. So this system is a coupled system. And what is interesting, I mean, if you go to Fourier space, actually, the first thing that one would do if you want to understand that, So we go to Fourier space, we assume periodic boundary condition, we use discrete Fourier transform, and so capital Q and capital R are just the amplitudes of the Fourier amplitudes of Qj and Rj. And if you do that, you end up with two coupled equations, which are still coupled. So usually, when you go to Fourier space, at least at the linear level, you hope that things are diagonalized, but this doesn't really happen. Indeed, the system is not diagonal. You have a still interaction in between the two equations. So the Q depends on the RK. So what can be done here? It's possible to diagonalize the system and obtain the dispersion relation. So, and this was done by a student, a former student of mine, is Andrea Pezzi, who found this canonical transformation, which maps from variables qk, rk to q tilde, and from p, which are momenta associated to qk, and g, which are momenta associated to rk, it's mapped to p tilde, right? So we get these new variables, q tilde, and you write down the equation for q tilde, and you have now two. It's valid for s equal plus and minus, and I will explain what is that. And so now you see that you have actually a real, harmonic oscillators. Actually, you have an harmonic oscillators for two branches in the dispersion relation, because actually we have two branches, the one we call plus and the one that we call minus, which would correspond to what is usually known as acoustic or optical branches in the dispersion relation. Here are just some definition of the constants, the beta and mu, which are placed here, but it's not relevant. What is more relevant is to go to the dispersion relation, to look at the dispersion relation, and I would like to show you the difference. So this is the dispersion relation just with waves propagating, which in the case of water wave would correspond to square root of gk, the hyperbolic tangent of kh. But what happens if you do include extra masses, so an extra resonators, so you put resonator, what happens is that you create a gap. And this is well known. This is nothing, it's well known to people that knows, but actually what you create are creating a gap. What does it mean? The presence of this gap actually implies that frequencies which are around 1, a little bit less than 1, a little bit bigger than 1, actually are not able to propagate. So there is no wave number associated to this frequency. So basically, waves cannot propagate with such frequencies. This is not by far it's not a new problem. People who have done quantum mechanics. For example, there is a classical example. It's a work by Koenig and Penny. Actually, the work is from 1931. And what they did, they solved the Schrödinger equation in the presence of a periodic potential, which is only dependent on space, not in time as our case, but it's just periodic potential. And what they obtained is basically that the energy has some gaps. So not all the energies are available. In the language of quantum mechanics, when we talk about energy, it means that it's actually corresponds to our dispersion relation. So this idea is actually of finding gaps when waves propagate in periodic structure is not new, but definitely the people who are working metamaterials, they just, that's their one of the main important things that they are doing. But what happened? Okay, so I think I have said. Okay, what I wanted to say also is that usually this branch is called acoustic, okay, and this branch is called optical. So optical branch and acoustical branch. So we have two branches in the dispersion relation. But of course, you can also work a little bit in a different setting. So you can work in a different setting because you can generalize this situation in which you have not just a resonator for each for each mass, but you have, a unit cell which contains small n number of masses, right? So you have a unit cell that goes from here to here. Then you can write down the equations, of course, and you can do diagonalization, and this is what Andrea Pezzi did, and you can find dispersion relation. So, and this is done, for example, for n equal to 4 or n equal to 5 on your right. So we have selected some values of the stiffness coefficient, just to, we set them to 1 without, going too much into the details, but we wanted to look to see what happened if you increase the distance, from the two masses. And what happened is that actually you start having extra branches in the dispersion relation. So, for example, if you have the unit cell of n with n small n equal to 4, you have 4 band gaps in the dispersion relation. If you have n equal to 5, you actually have 5 band gaps. So basically, this is one of the main things that is actually happening in our device, although we are not able to do such a quantitative study. We are, at the moment we're working on it, but that's what we are not able to do it, in the sense that when we place resonators underwater, what will happen, we somehow have some evidence of that some frequencies cannot propagate through the waves. And so this will, make waves, they will be reflected, or they will be, basically reflected, or they will be dissipated, because in our case, we have dissipation because of water. It's a viscous fluid. Okay, so this is the, let's say okay, and then we go from Kelvin chain. By the way, this is called Kelvin chain. This has been studied when you have for each mass, you have an extra small resonator. It's called Kelvin chain. Actually, Kelvin did already study this, already discussed the two branches in the dispersion relation. But now we go to our case, in which this is a continuous case, and these are our pendula, which can oscillate. And but it would be the same thing if you can think them as a mass that is attached to a spring and just can oscillate in this direction. Okay, so let's try now to see what is the if there is something that works. I have presented this, and of course it's we were very curious to see what happened if you go in a wave tank and try to do some experiments. Okay, so we did experiments at the Politecnico di Torino, which is the other university in Torino. We have two universities. One is the one where I'm working, so University of Torino, and the other is Politecnico di Torino, which is an engineering school. And but the good thing is that they have a very nice wave tank, which is 50 meters long. It can be up to it's 60 centimeters wide, and it can be filled by water up to 1 meter. Okay, so basically those are the features of the tank. What we have done, we have anchored, and this is basically you'll see it's one-dimensional propagation of waves, basically, right? Because you have a wave maker here, which generates a single piston, which generates waves that propagate to the right. And as you will see, and then what will happen, and we put this, but we didn't actually put spheres, but we put cylinders with their axis parallel, perpendicular to the axis of the tank. And the idea is we didn't want to break the symmetries of the waves, in the sense that we're working with long crested waves, so one-dimensional propagation, and we didn't want to introduce, some disturbances in terms of diffractions or other problems. So we put cylinders. So we anchor each of them you can think of it as a cylinder. So we measure waves using different wave gauges. Placed at different locations. So this is wave gauge 1, this is 6 wave gauges here, and there is a wave gauge here. So those are the wave gauges where we bought them. It's just a commercial system from Edinburgh Design, and they have an accuracy of 0.5 millimeters. And they're the resistant type. Wavemaker is a piston type, is Delft hydraulic, and of course you can program, you connect this Wavemaker with a computer, so you can program your computer in order to move the Wavemaker, and you can create regular waves in a range of frequencies and in a range of amplitude. So everything is written in a MATLAB scripts. Okay, so this is what actually looks like. This is the tank, and those are the cylinders that you see here. We anchor them with metal wires, and we put them some extra crosses here to avoid, lateral motion, transverse motion. So the idea is that the cylinders would be allowed to move only, with their axis perpendicular to the direction of propagation of the waves. I have let's see if it works. If not, it doesn't seem to work. But I'm sorry. I can just go to here. Do you still see?
Yeah.
Okay. So this is a classical example, right? Okay, waves are generated from the left. This is a quite high, strong waves, okay? And waves are generated from the left and they propagate to the right. Although your perception, as you will see, is that, if you wait just a second, is that waves looks like they are propagating actually from right to left, actually. But what is happening is that those waves are actually reflected. So you see a big reflection from the device. As I mentioned, this is quite strong, so you see phenomena of wave breaking, which are by far hard to understand. But at the end of the story, if you go at the other end, so those are 11 cylinders. If you go at the end of the wave tank, what happens is actually that you see that there is no, basically, let me just go here to show you. There are just very small waves, very small and long waves. So basically, in these cases, which we have shown you, the device does basically. Oh, now it works, right? Okay, let me just. There is also. And okay, but we have seen this. So now we have done a very large number of, well, not very large, but a large number of experiments. And what we did, we changed number of cylinders. We changed the distance between cylinders. All of them were multiple of some L stars because those cylinders were anchored on rails, which have holes at the distance of 11.75 centimeters. So basically all the cylinders were placed at a distance which are multiple of L star. We also selected different distances from the undisturbed water level. As you have seen in some cases, the cylinders can be uncovered because waves are too large, so they are getting contact with air. The amplitude also, we change amplitude of the waves from 1 centimeter to 3 centimeters. And we send, what we did mostly, we send monochromatic waves with frequency from 0 hertz to 1 hertz, which is basically what the Wavemaker at the Politecnico can do. And what we did with the data. So we measure surface elevation before and after. Of course, when you measure at the last gauge, the one after the device, right away you can measure the transmitted wave. But then, if you want to, it's a little bit more tricky to understand the incident and reflected waves, because you need a number of gauges. You need to do some work. But you can follow papers like from Goda, who tells you when you have a number of gauges how to decompose your system of waves going in one direction and the other direction. And once we have incident and reflected surface elevation, we can compute the coefficient of transmission, coefficient of reflection, and we can compute also the dissipation. The dissipation will be 1 minus coefficient of reflection minus coefficient of transmission. Okay, so basically what you will see in the presentation of my data is basically these coefficients of reflection and transmission and dissipation. Okay, well, this is just an example of incident wave decomposition, but let me go to the interesting part, which are the results. Okay, so first of all, and by the way, this is work that has been published recently, well, it's 2023, by Matteo Lorenzo, who was a student, PhD student of mine, and collaborators. And so here what we did, we ran waves of 1 centimeters at a distance of 12 star, and we placed from 2 cylinders to 11 cylinders. 11 cylinders was the maximum we could place, right? And what you observe here, of course, this is coefficient of transmission. So you would like to have this coefficient of transmission equal to 0, right? That would be the goal for all frequencies. You would like to minimize the coefficient of transmission. And what is clear here is that when you increase, but as we expect, the number of cylinders, the coefficient of transmission decreases. But what is also clear here is that you have a minimum here around 0.6 hertz, minimum of transition. And this minimum of transition actually corresponds to the frequency of oscillation of the cylinders, in the sense that cylinders oscillate. I mean, they're free oscillation. If you move them from their equilibrium position and you let them oscillate in the water, they have a frequency of oscillation which is typical of, which is about 0.6 hertz. So this dip here that you see here, in which transmission is almost 0, is actually related to the local resonance effect, as we have seen, in the sense that when waves propagate and they have the same frequency of oscillation of the pendula, they will transfer energy to the pendula, which will start. Part of it will be reflected, but it will be will be then the pendula will create a wake and will become turbulent, and it will be dissipated into the water. Okay. Okay, so this is dissipation. Indeed, dissipation is quite big. As I mentioned, this is the coefficient of dissipation, and in this case, you have very large dissipation around 0.6 hertz. Okay, so well, this is we change. I mean, those are a number of graphs. We change also the distance from the water level, equilibrium water level, from 0. If you put them floating, that changes the frequency of oscillation. It lowers it, and that's why you have a dissipation which is much larger at lower frequency. But then you see that for the distance of 2 centimeters, 4 centimeters, or 6 centimeters, you still have this big peak of dissipation. A little bit of high frequency things changes, and of course, yeah, things are a little bit different. And it's clear that, I mean, you dissipate more if they are closer to the surface elevation, right? The 2 centimeters closer. Okay, let me skip this. There is also another phenomenon, as I was mentioning, which is the Bragg scattering effect. And this is typical when you have the interaction with periodic structure. So when L is the distance between two pendula, so it's 2 pi over KL, wave number KL. This Bragg scattering is ruled by some sort of conservation law, but I mean the following condition: if you have two waves, K1 and K2, so you have Bragg scattering when K1 is equal to K2 plus KL. So well, yeah, that's what is a typical interaction between two waves. It's a three-wave interaction, so it's not actually two waves plus a periodicity due to the distance between the pendula. And if interaction becomes stronger, resonant condition holds. But of course, those things don't. I mean, it's not actually. We're assuming that the pendula are not moving, so omega-1 is going to be equal to omega-2, and basically the solution means that K1 is equal to minus K2, which actually implies that waves are reflected, and this happens when the distance L between the pendula is equal to the wavelength over 2. So, or you can have a higher order interactions, which comes actually in this form when L is equal to n times L lambda over 2 with n an integer. Okay, so this is actually what we look at in our wave tanks, and you see you can make predictions also for all the higher order. Once you have F1, you can calculate the Bragg scattering F2, the frequency of Bragg scattering F2, and so on. So all these vertical lines are the different Bragg scattering prediction for different distances. So of course, the Bragg scattering depends on the distance between the pendula. Okay, so for example, a 6L star, so 6 times 11.75 centimeters, the Bragg scattering is predicted at this frequency. For 9L star, you have prediction of this. This is the first one, and this is the second one. And what is interesting to look at, if you run experiments, if you compute the reflection coefficient, actually you see a big, maxima exactly around the prediction of Bragg scattering. So actually Bragg scattering is really happening in our wave tank, and that's why we have a lot of reflection. Okay, so this is the case of transmission coefficient, reflection coefficient, and dissipation coefficient for different cases. Okay, another case, but just because I don't know how much time I have, Francesco, because I'm running a little bit long.
Minutes.
Sorry?
Another 5-10 minutes.
5 minutes. Okay, I will do it. So basically, I mean, so the idea now is to we want to minimize the transmission coefficient, right? So the goal of this is to minimize transmission. So you want to minimize transmission for all frequencies, right? Not just for the resonant frequency. So we have to play the game in which we have to try to include some Bragg scatterings in our data. And so the way we did it is to try to do what is called as grading. So we place the distance, we place the pendula at some distance which is not equal, in the sense that, well, the first two, the three have the same distance, but then the distance increase. So the first is 6L star, then you have 7L star, 8L star, and 9L star. So that was the maximum. And also we did reverse, okay, so at 9L star. And the idea, as I mentioned, is to try to minimize the coefficient of transmission. And this is what is happening, okay? This is transmission. I'm just concentrating on transmission. You see, it goes from 0.4 actually to 0.2. We have basically transmission is reduced to 20%, only 20%, and in some region even lower. And we have, in this case, we have 9 pendula. These experiments were done by only with 9 pendula, not 11, because they could not fit in the rails that we had. But the good thing is that really we were able to, reduce by using this grading transmission to a whole range of frequencies. Okay, without going into the details, I just want to mention that Francesco De Vita and colleagues, and Filippo De Lillo, Roberto Verzico, and myself, and also with Federico Busia, we did some numerical computation. I mentioned, I mean, this was all developed by Francesco and also Roberto Verzico, who developed a code for, which is not trivial at all, because you have free surface plus moving objects inside. But we were able to run simulation and look basically at similar things. And now, yes, I don't want to go into the details of this, but this was done with periodic boundary conditions at the beginning. We looked just at the decay of the waves in a periodic domain, and you see how things. Capital omega is just a ratio between omega resonator and omega wave, and you clearly see that of course when omega is equal to 1 or close to 1, so when the frequency is the same, the energy decays faster in all these cases, right? And you can see also those are space-time plots, and so you can see that, for example, I mean, if cylinders are fixed, actually there is not much of reflection, and so waves don't seem to change their direction of propagation. However, if actually you have some possibility of oscillating, you see this is space and this is time, so the line indicates the velocity, the slope indicates velocity, and it's clear from here that waves are at the beginning are propagating in some direction, but then they change direction. So this means that they are reflected. This is a periodic domain, so this is not the whole story. Now, Francesco has developed a code. Let me go again to and this is the last slide to show you what Francesco, okay, is here. Francesco has done. So he developed a code, so an Navier-Stokes solver in a wave time configuration. So this is just should be spheres, well, cylinders. Actually, this is 2D simulation. But again, what you see here is that waves are mostly reflected, and this is in the simulation, are reflected, and the waves that propagate here are, well, less big than, they're smaller than the waves that are on the left-hand side. So that's where we are. We are actually working on also on DNS on this, and there are also a number of things that we are doing. Let me just go back. Oh, it works for some reason. Okay. You see the form, this is just because the aspect ratio has not been kept. So that's why this R should be circular, but they are actually oval. So conclusions, and so we have developed a new device for attenuating surface gravity waves. It's based on concept of metamaterials, works on two mechanisms. One is local resonances and the other is Bragg reflection. We did some experimental and numerical work with some success. I'm not saying that this is the best and this is at the end of the story. There is some potential to do, there's some potential for attenuating waves. And we have also made some sort of optimization, we made the grading, so it seems to be an optimal configuration. But of course, the real problem, as Francesco knows, when we go to move from 2D to 3D, physics can be different. So that's where we are at. So we need to do experiments in a 3D wave tank where waves are characterized by a full spectrum, and actually cylinders become spheres. And we want to redo experiments in this new setup. Okay, that's it. Thank you.
Thank you very much. Thank you. So, any questions from our friends online?
Yeah, I have a good question, if I may.
Yes, please, Domenico, please.
Yes. So if you could repeat, I don't understand where the different branches came from in the dispersion relation when you modify the Kelvin chain.
Yeah, sure. Okay, so now this is the okay. So the setup. Okay, this is just the standard chain, right? So this is a standard chain, and waves propagate here, and then this dispersion relation. I guess this is clear to you, right?
Yeah, right.
Yeah,
that's fine.
So now let's assume that you put an extra chain, an extra mass, and a spring. So but this is still one-dimensional problem, and you write down the equation of motion just in this setup. Okay, you write down the equation of motion and in a conservative manner. Okay, and so basically you want to find the dispersion relation associated to these waves. That's what you want to do. And the way we did it, there are many different ways of doing that, but the way we did it is just we moved to Fourier space, and we wrote equations in Fourier space. Those are linear equations, and you end up with two coupled systems. One for the masses, red masses, and the other for the blue masses. But they are coupled, so you need to do an extra effort, and you need to diagonalize the system, and you actually find the eigenvalues of the system. So you find the frequencies, and those frequencies are given here, and are two of them. So you have plus and minus, which are inside here. So basically, you have the sum of and difference of these two functions, and those two functions are just omega k is the standard dispersion relation, plus square root of chi, which is the stiffness, the mass, square plus the stiffness over the mass. And if you plot that, this is what it looks like. So it's just the dispersion relation associated to the system. There is nothing, I mean, special. The way we did it is somehow interesting because this was very helpful to work for the next problem, which was this one. So we needed to diagonalize the system, and we like to do it that way. But it is just a standard way of finding eigenvalues of a problem of this set of equations.
Okay, thanks. I had another quick question regarding the movie that you showed. In the movie with the experiment, the cylinders are actually at the water level. So does it matter whether they are at the water level?
As I mentioned, I mean, we did many different experiments. This is one, as I mentioned, is one of the strongest with largest waves and with cylinders which are very close to the surface elevation. So of course the physics becomes very much more difficult, right? When you have, because waves start breaking, because you have regions in which you have waves where the cylinders are uncovered and you have just contact of air with the cylinders. So yes, I mean, physics can be much more complicated in this case. We try to avoid that. I mean, I have shown you this movie just for the purpose of showing you the effect of reflection, which was very clear from this movie. But most of the experiments that we have done with waves of amplitude of 1 centimeters were actually characterized by cylinders which remain underwater for all the time. Okay.
Thank you. Thank you.
Other questions from our friends online?
Francesco, can I ask a question?
Yes, please. Hi, Emiliano. Hi.
Hello.
Miguel,
Hello.
it's Emiliano Renzi from...
Emiliano. Hello. Hi. Nice to I mean, I don't
nice to see you again after many years now.
Many years. Yes.
I remember you came in Dublin when I was...
I was in Dublin, yes. I want to see again my... if I can see you okay. Okay, it's okay. Oh, Emiliano. Okay.
Emiliano, maybe Emiliano, you can share your screen. There you go.
It's okay. I mean, just go ahead.
Yeah, so the question I have is regarding, this, as you mentioned, these two different, maybe it's working now, yeah? Hi. These two different mechanisms for reducing transmission. So one, if I understood correctly, is related to turbulence, and the other one is related to more to really diffraction, and Bragg scattering, which is linear. So did you have a way of sort of weighing which one is more dominant, for example, in your experiments?
Yeah. Okay. So the local resonance has double effects, has two effects basically. So it's not just turbulence, but it's also reflex. So because you have seen that you also in the presence of just local resonance, you can have a reflection by a single cylinder actually. A single cylinder can, but then. And indeed, in the system, in the toy model that I present to you, there is no dissipation. So you think things work also in that case. So, which is more effective? It seems to me that this local resonance is strong, right? It's well defined. You have always a big peak around this local resonance. Bragg scattering, you have to tune things, right? You have to make sure that your wave is, some multiple of the distance between the two devices, the two pendula. So it's a little bit more complicated. But at the end of the story, if you do the grading, it seems that things are more or less comparable in the sense that in both cases you have some, transmission which is low, but it's actually slower for the dissipation for the local resonance. For the local resonance, its transmission goes really low, up to 5% or less, right? I guess this local resonance is basically the one that is used for for wave energy converters, right? You are actually always looking for some resonance with some device with waterways in order to extract energy from. So there are similarities indeed with wave energy converters and then our device, but we just want to use it for protecting coast, but I don't know how far we'll go. I mean, in reality, right? Because when in a lab things are nice and scientifically, I think we learn a lot. There are lots of interesting. There is a lot of interesting physics. But when you have to go in the ocean, you have to scale those things, and you have to divide, have an object which is 2 meters of diameter, and everything becomes much more complicated. And we don't know. I mean, we wrote the project and we wanted the European Union to fund us to keep going and do some experiment in real ocean or Mediterranean, but at the moment without success. So we are working on a 3D wave tank.
Other questions from the classroom? Hi, Miguel. Yes, I mean, maybe I gotta go to teach the AI group study, but very fast, about negative mass conditions here of your system, and when you did the variable distance of masses, you did the case, to varying the distance between the oscillators.
Yes, yeah.
Mm-hmm.
In the model or in the model or in real?
In experiment.
In experiments, okay. So we yeah.
So how would you then? I mean, the periodicity is broken, is right? So the band gaps they still survive. So how would you?
I don't know. That's exactly. Indeed, it's very interesting. It's very interesting what you're mentioning. I mean, this is because what we are doing actually. The classical Bragg scattering, so these band gaps which are associated with Bragg scattering reflection, actually are obtained with fixed structures, but our structures are moving, right? So they are moving, but incredibly, that we also run some experiments with fixed cylinders, and Bragg scattering was much less evident. So there is some collective motion of this pendula for which reflection is much higher when pendula are allowed to move.
Yeah, this
mystery for me. For me, this is still a mystery.
This reminds me of the feed-forward neural networks. So what you have here, actually, you can imagine you have a neural network with different layers, but each layer have a different distance. So that you're kind of doing from large to small scale dissipation. So basically, the initial pendulum, that are very far apart, maybe they will take care of dissipating the longer waves. Then they move forward, and then they are the layers with the pendulum that are nearby, and they will dissipate the smaller one, and so on and so on and so on. So basically, you can even think it eventually. Maybe there will be in the continuum. There will be a PDE that is going to govern the space-time evolution of the wave field through this non-homogeneous system of oscillators. So
yeah, possibly yes. I mean, it's mathematically. I mean, we haven't done much. So it's if you have any idea. I mean, numerically yes, but mathematical approach actually we didn't do much. So everything is welcome.
No, I'll send you an email about it. And negative masses.
I don't know what do you mean by negative masses.
The fact when you have the pendulum here, because here you're doing a cylinder, is right, which has an extension.
Yeah.
So when you're gonna go in 3D, you're mentioning about doing spheres.
Yes, we're doing
now
spheres.
the effect, the forces that the water exert on the sphere, they would be much less compared to an
Probably.
elongated, and so maybe, you know, I don't know. So if the maybe you will
The added mass, okay, an added mass, okay, yeah, that's
yeah, the added mass basically is negative.
yeah, the added mass, yes, true,
and,
yeah, and so we surely, I mean, we are expecting to, you know, to see some changes, maybe something less effective, but we still hope to see something working.
And then in metamaterials, they talk about defects, you know.
Yeah.
Imagine that you're gonna make one cylinder a little bit bigger than the other, then you can have all these localized structures. You know, I wonder if, you know, this you have seen it experimentally.
Yeah, we haven't you know, go that far. So, but it's sure that we I mean, there is plenty of things to be done, I guess, before. You know,
No, a very beautiful work. I mean, how many years did you work on this? How many people are working with you on this?
Okay, so the first experiment were done by one of the main experimentalists who actually did most of the work is his name is Paolo Pezzuto. You may know him. Paolo is connected. Paolo has, you know, started about probably 3 years ago. We started, or 4 years ago. We started 3 years ago, maybe. But then and then, you know, we did some experiments, and Matteo Lorenzo did his PhD. But now Alexander Kane from well, he's from Lille at the moment. So from Lille, he came here. He did other experiments and other colleagues. So it's been 3-4 years of thinking, let's say.
Beautiful work, beautiful. Okay, thank you very much.
Thank you, Francesco. Hope to see you soon. Ciao.
Yes, thank you. Bye bye. Ciao.
Thanks to everyone. Ciao, ciao.
Thank you. Bye.
Ciao.
Okay, let's go downstairs because they're waiting us. Very interesting.